Aloha attendees. Thank you very much for coming. This is going to be a really interesting panel. I just want to tell you that if you and your Ohana and your colleagues and friends were not able to attend this because they were doing something else, it will be available on the YouTube channel on the Better Tomorrow Speaker Series, probably next week. And then eventually we will be having a highlight version on our website, which will be up for at least a year. So there'll be lots of opportunity to catch up with this. My name is Roger Jelinek. I'm Executive Director of the Hawaii Book and Music Festival. And I have a special relationship to our speaker, Patrick Sullivan, because I had the privilege of spending every Friday afternoon for about 5 years working on this book. And you think that's a long time, but he has a lot to say. And to get it down to manageable proportions is an epic task. But in this panel, we're going to let him go, and he's got a fascinating ideas to give you. So without further ado, I'm going to have Patrick introduce himself, and then off we go. Aloha.
Aloha, and thank you, Roger, and thanks for putting this together and your dedication to this Hawaii Book and Music Festival too. So it's doing really great. Appreciate it. And I'm delighted to be here today. So I started Oceanit 30-some years ago, 36 years ago, and over time I developed this approach that I'm going to share with you today on disruptive technologies and how we think about it. But a little bit of my background, I met a local girl, got married, got my PhD here at UH in engineering, and really was torn between either working at Pearl Harbor or at the university, so I started Oceanit. And over time, we've created an interesting group. Right now, it's a few hundred people, maybe 100 plus PhD level scientists and engineers. So we practice what we do and what I'm going to be talking about. And I share it in the book. The thing in the background there behind my picture is this thing we call the petting zoo. And it really started because I realized that although, we're downtown Honolulu, and I know most everybody, most of the businesses and everybody from the banks, insurance companies, and architects, and everybody, they really didn't understand how this worked. And so we put the petting zoo together just to show people stuff, what happens when we think of things, and to draw this connection between education, ideas, and things you create from ideas. So there are technologies we put on the wall, and we have, during non-COVID times, we had a lot of schools come through. We still do. A lot of businesses and visitors from all over, actually visitors from all over the world. We work in so many industries now. So we work in energy, defense, healthcare, industrial technologies. All this was really created here in Hawaii from these ideas in this process that I'm going to walk you through. But that's what the petting zoo is. And you see it in the background there because it's in the office, but it turns out it's kind of a fun thing for people to go and pick something up and try it out. And there's some of the things, for example, when we started, I'm going to talk a bit, not to get too ahead of myself here, but some of the things I'll talk about are nanotechnology. And so we made things, changed surfaces to act in these peculiar ways. We made almost little toys to play with, and we still have some of those on the wall too, because it's kind of like, you roll a bead of water on this thing, you think, wow, that's really weird why it does that. And those are some of the early things that go into this innovation process. But those are things we make, and some of those are actual technologies we actually go and sell commercially today. So it's a wide range of things. With that said, I thought I would share some slides and walk you through how we think and and then I'd like to be available to answer questions. But let me try this here. And share. Okay, hopefully you can see that. And so it's really how we create these disruptive platform technologies. And I thought I would start with this idea of what a platform technology is. And this is kind of out of the internet. It's really technologies, a group of technologies used as a base or infrastructure for applications, technologies, and processes. So what you've got on the left is this idea of applied research. We call it fundamental research. Again, this kind of comes from something that's online. You create these enabling technologies, you produce things, and then you create a variety of products. And this is something that has been going on forever and ever. And it's something we do, and we're actually pretty good at it. But what's interesting is it's something a lot of people can do. And when we do this, we're kind of creating these big opportunities. And then, of course, doing something about them takes quite a bit of work. In this one, I wanted to kind of give you an idea, an illustration, what I'm talking about when I say disruptive platform technologies. So a really good example is kind of illustrated here with the transistor, which most people think sounds, it's kind of pretty common, but it really wasn't. And the solid state transistor, as seen here, doesn't look anything like the transistor you see in the middle. And it created enabled all these things on the right, from Teslas that are like computers on wheels to iPhones and everything else. And the reason this is important is because before this happened, it was hard to imagine what could be an iPhone. You can't really predict the iPhone, but the fundamental science that went into this is what created the opportunity to produce an industry that created trillions of dollars and millions of jobs and transformed the world. This happens over and over. And this is what I mean by disruptive platform technologies. And in the context of what we do at Oceanit, because we're here in Hawaii, we can do this from Hawaii just as well as we can do it from anywhere. And we do. Now, in this case, it was interesting because Shockley was one of the key guys, and he and his colleagues got a Nobel Prize in 1956 for this idea, this insight. Now, if somebody said to you, I've got a guy who does quantum physics who's now looking at semiconductor physics, you say, well, what's that got to do with the price of corn? The fact is it doesn't, but what it did do is it created the future. And it starts on the left. And so what's more interesting is that when he went back, so he grew up in Palo Alto, his father was in mining, and he was a difficult guy, so I've heard, as are a lot of the really smart people. We got a bunch of them here. People that are super smart are socially sometimes awkward. Don't be surprised. But what's interesting, he went back to Palo Alto, ended up as a professor at Stanford, but there really wasn't a tech industry or anything like that. It was mostly agriculture. And it's hard to get people's heads around that idea that it didn't exist in its current form. And it was some of his students, that it really created Fairchild, which started making semiconductors and transistors and created industries, Hewlett-Packard. There's a genesis of how this happens, and you can map it back to those things. But they were mostly in agriculture, and it was a nice university. It wasn't what it is today. Things change. And I can trace this kind of thinking back to so many places. One of my personal experiences was at University of Colorado in Boulder, where I did my undergraduate. And at the beginning of the early days in semiconductors, my job was at a company called Storage Tech. And we used equipment at the university because we had mostly farms and cows in Colorado and in Boulder. things change. And so for people, it's especially in Hawaii, but everywhere, it's important to kind of get your heads around how things change. But they start with these interesting ideas, which goes to what we do. We call mind to market. We think of things, as you see on the left, is the opening slide, but these areas we call transdisciplinary mind, transdisciplinary thinking. And then we have a process to move them into the marketplace. And that's what's talked about in the book. This is how we start thinking about disruptive innovation, things with high pain and low certainty. So it's a little counterintuitive because there's nothing wrong with application innovation. So I've got a red pen, I make a blue pen, and there's a great market for blue pens. That's a wonderful idea, and it could be a great market. What we're talking about is how do you frame up something that is worth your effort to try, even though it's never been done. Something with high pain, which means somebody has to fix it, and low certainty. So by high pain, an example I've used is, if an asteroid's going to destroy the planet, we'll send Bruce Willis because it's better than nothing. And we've exploited this idea, but this is how we start thinking about it. And we've created this concept of a portfolio to manage risk. A lot of economists talk about portfolio management and risk. This is a risk-adjusted portfolio of technology and broken up into these buckets of interesting, challenging, and disruptive. So there's three flavors of risk. There's technology risk, execution risk, and market risk. Roughly half of the risk is in market. So if you think about that for a second, if half of the risk is in market, it's kind of a crapshoot when you start something. Is the market going to be at the right place at the right time where this could matter? It is a real issue. The way we manage it is with a portfolio. And it's hard to manage a portfolio like this, but that's literally what we do. This is how we pay the bills as we grow what we do, but we manage risk like this. And it skews to disruptive because it turns out we're pretty good at it. And we have a process. I'm going to share some of that with you. I'm not going to spend a lot of time on this, but just to give you a more complete idea, we've got the blue zone, the deep science part. It's a culture in and of itself. It's around curiosity, discovery, exploration. And then on the right, you've got the green zone, which is really around the product and end users, things that people can use that matter to them. And it's separated by this thing we call the rock and roll zone, because it's a highly nonlinear connection between these two cultures. Now, we use design thinking to create a common language between these cultures, but this is what we do, manage this environment. And by using a common language, we created an appreciation for why one person in one zone is important to a person in another zone. And it kind of addresses an issue. A lot of universities and national labs, for example, 90+% of everything they do never sees the light of day. And that's not the case here, but that's because there's no cultural appreciation. There's no common language in between what they do and the rest of the world that actually could use what they've got. I'm not going to go through this, but I put it up there to show you there's actually a process. And the two key things kind of to take away is this idea between convergent and divergent thinking. Divergent thinking is kind of open, blank piece of paper. And convergent thinking is where we kind of say, now give me a thing by a date. So it's this combination of those two that we manage, and it follows this process. I talk a lot about it in the book, but I'm not going to spend a lot of time on it today because I've got maybe a higher level way to talk about it, but hopefully to bring people through this so that maybe it's something that's accessible that you can think about and try to deploy or to work with. Starts with a relatively simple idea about asking a question. And we do this in the fourth quarter of the year. The question is really about, what are we doing with our time on the planet that's going to matter? And that's where it gets to a hard problem of asking a good question. But it's really a question of what's interesting and important. And that may as I've explained this to people, and I've been doing this for 30 years plus, it seems pretty hard to do, but what I discovered was a lot of people don't give themselves a chance to actually think about these things. And thinking about these things is one of the key operative items. So asking a good question about what's interesting and important is kind of the first step in the process. And it's not about geography, it's not about Hawaii, it's not about the US, it's about the planet, it's about what's going on in the world. It's not limited by science, it's not limited by politics, or it's really about what's going on the planet that we should think about. It's not a simple issue either, so this is not an easy thing to do, but it turns out if you do this in a disciplined way, you end up with some really interesting things to focus on, and that becomes the beginning of what we do. And we do this every year, and this lends itself to creating tons of stuff all the time. We're going through that now. What is interesting and important, and it's a lot of fun, but not everybody is comfortable doing this. And I think part of the reason is because they're not comfortable thinking. They kind of want to be told what they should do versus giving them this open idea of what to think about. Now, we kind of follow this process, and this is where I get a little more technical and I'll spend more time. Ideas, programs, projects, products. That's kind of the migration of what we do. And these little boxes or bubbles here are kind of how we fund it. So we've created enough capital at Oceanit. We fund our early ideas because they're generally way too risky for anybody. On the left axis is risk. On the right side is benefit, and then on the x-axis is time. So the risk is quite high in the beginning, but over time we drive that risk down. And over time, the benefit in the beginning is nothing, but in time the benefit goes way up. That's what we do. Now, the way I've laid this out, it kind of, to a large extent, disintermediates venture capital, because venture capital has a place, as you see with this kind of red bubble here, but because we don't have venture capital here, and by the way, what we do is way too risky for them to fund. They're really not risk takers. Venture capital works best when everything is fully baked. It's just put in money, turn the crank, and make more money. That's kind of what they're built for. Well, no matter what they tell you, that's honestly my experience with it. But we start with this area of ideas, and ideas are so important. But ideas are things people are almost afraid of. So it kind of looks like this, right? You've got the left side here is really research and development. The right side is more commercialization. And again, we start with what is interesting and important. And a lot of people jump ahead to requirements, especially people in the government. If there's no requirement, we can't do it. If there's no requirement, we don't have any money for it. In the short term, that might make sense. The way we're looking at it doesn't make any sense. Generally speaking, when we start with interesting and important, it precedes requirement pretty much every time. It's weird how that happens, but it always does. And then you get to the commercial driven things around projects, and then real growth around products. And growth around products is around scalability. Right? So how do I produce a product and make replicates and scale in a cost efficient way that people can use that matter, makes a difference. So, commercial is where you start to look for financing things, and there's all kinds of ways to do it, including venture capital, but there's a lot of corporate co-development we've been doing. And of course, everybody focuses on the boom, the hockey stick growth. That's what everybody wants. So you put in money in turn, and that's the explosive growth that really drives venture capital. And there's a place for that, but it turns out it lives in a few regions of the country. Really, you could say 8, but maybe 4. It doesn't live here. It doesn't live in most places. And so we've created these ideas that may work with private equity or venture capital. We've done some private equity deals or VC deals, but to not require that to make progress, and not require that to get to market, or necessarily require that to scale. So again, back to this question of what's interesting and important. So we develop these ideas, and then we go to different parts of the government to ask them to fund it. And they're generally ideas that are not fundable by anybody else because they're just too risky, right? We'll think of things that maybe they know are problems, but nobody's put forward an idea. And it's about matching what we call risk appetite. So risk appetite is for these different federal institutions. It's Department of Defense, it's NASA, it's Department of Energy, it's Department of Commerce, pretty much every federal agency. And they go up and down. They're not always risk adverse. They're not always, willing to take a risk. So it varies quite a bit. But they invest a significant amount into early stage research, and they take a chance on ideas. And so we may spend a lot of time educating them about why they should underwrite an idea. And one of the ideas I'll be talking about in what we're doing with our test for COVID and this idea of mathematically designed therapies, for example, we spent about 1.5 years trying to educate DARPA on why they should fund it. DARPA, Defense Advanced Research Project Agency, is considered the high risk arm of the Department of Defense. They can be really wimpy sometimes, and they're really not always willing to take a risk. And so we may have to convince them it's worthwhile in order to produce a profound result. So we actually did that, and I'll review that in a bit. But there's several agencies that will do this. And right now, for example, Department of Energy is really pushing hard on climate. They will take a risk on things that nobody will. Department of Defense has certain critical problems they will take a risk on too. Again, going back to this problem of, again, it sounds almost trite, but if a meteor is going to hit the Earth, if you don't send up Bruce Willis, hopefully you got an idea, a better idea, but you better do something. And so we think about those things. But anyway, the government will put money into those things, and it's a really important thing. And by the way, this is historic. This goes back over time and pretty much everywhere. And on top of it, what's interesting is we work, for example, with Office of Naval Research, ONR, which is really the oldest research organization in the U.S. And they will underwrite ideas sometimes. They fund universities and national labs and things too. But there's agencies out there that are really trying to think hard about how to make a difference and solve a problem. Now, I'm going to start with a nanotechnology journey, but I thought I would kind of put this up here because this is a nano surfboard. We were talking about nanotechnology a long time ago. We thought it was a really interesting and important thing. And I said, let's stop talking about it and make something. So the surfboard on the left has titanium nanotubes. We made one. They're quite expensive. It's much more resistant to dinging. But that was important because what it did was break down this barrier of going from PowerPoints and just papers to make something. Make something is a really important step in the process. Even if it doesn't work, even if it fails, even if it's not the usable thing you think it should be. There may be a market for this kind of surfboard, but we thought it's probably not the market we're going to focus on. But we literally made the surfboard and we broke through a kind of a glass ceiling of people dancing around an issue as opposed to doing things. And once we did that, it opens up kind of the floodgate. And so I'm going to walk through some of these things and give you some specific examples. So we started this area in nanotechnology in mid-2000s. And we hosted an event with the university. And for example, the Nobel Prize for carbon nanotubes, Sir Harold Kroto, was here in the office. He was an invited speaker. We went up and said hi, and we're looking at this stuff, spent some time with him. We got to meet some of the smartest and most interesting people in the world. It was really this area where we thought this is something we should do. It really wasn't a lot more than that, except we thought we should do it. And so that led to a lot of interesting things. Now, we produced an idea for the industrial application in nanotechnology. And part of that was because around the same time, I remember I was at a conference, and there was a MIT had a very cool display of ketchup coming out of a bottle with nanomaterials, and the ketchup flowed right out, didn't stick. And there was somebody there from I think it was more of an industrial energy business, and they kind of rolled their eyes because it's like, well, the ketchup bottle is cool, but that doesn't help me. And around the same time, we were thinking, and there was an issue in Hawaii about bracking base realignment and closure, Pearl Harbor. So it seems like an unthinkable thing. Lay off 5,000 people and do all the ship repairs in Maine. That was a real issue on the table. I know that's hard to fathom today, but these things happen. And so we said, what if we produced an industrial version for shipyards? And we went and convinced O&R and others that that would be a good idea. And it was interesting because they were locked in a maybe 50 years ago of thinking, maybe longer, in how they did business. And so we explored these ideas. And out of that came all these projects and really interesting early products, things we did, we made. And I'm going to review some of the things we're doing today, but that's kind of how we started out with this. It was an interesting and important idea, which we thought we should do. And we had all kinds of cool stuff we thought we'd do, but then we were looking for, okay, where would we focus? And this industrial area was something nobody really had a handle on. And the ketchup bottle was cool, and there were some really cool things. But other than that, there wasn't much going on except this cool stuff. And we thought, okay, what should we do? And so one of the things that happened roughly as we were starting, I remember, was the Macondo Deepwater Horizon oil spill, $50 billion accident. I remember meeting with the guys from British Petroleum, and we had the whole R&D team in Houston and the R&D team from Britain on the call, and because they're a British Petroleum is a British company, obviously, and realized they're kind of living in a time warp. This thing, the failure occurred because of a problem around steel and cement that worked its way loose. And so we thought, okay, what if we could do something about that? So we literally put together an idea to improve the bond strength. This is a project we did with Department of Energy, Shell, and a bunch of others. It was a kind of a hui, and we within 18 months went from the lab to a full scale up and deployed in the Gulf of Mexico. Built a factory in Houston with nanotechnology. We learned from the work we did with Pearl Harbor and the Navy how to dial in surfaces. Pick a surface. What do you want? I can engineer one. And this was really interesting because we had a few months to put something into a well in Pennsylvania, and then a few months later to build a factory in Houston and to put that actually deployed into the Gulf of Mexico in the most aggressive wells in the world. Now, we're not really, we're kind of green energy people, but this was a huge problem. And the crisis that we got sucked into was kind of interesting because, so much was going on at the time. The whole Louisiana coast was devastated. And I remember the guy at Shell saying, I got 2,000 guys here with PhDs, and they write papers. I get nothing. He said, if you do this, you're my new best friend. And we put this together, and we became very popular with the whole industry because we delivered it and executed the whole thing in 18 months. But it really started, again, downtown Honolulu. We've got different versions of stuff we've been doing. We have another nanopolymer we use on heat exchangers. This makes heat. So every power plant, every thermal power plant in the world, in the entire world, uses a heat exchanger. We make them more efficient. This saves energy, saves carbon, saves cost. And now we're starting to deploy this around the world now. I mean, between the US, Europe, India, and other places, we're starting to roll this out. Aeropel. This is another kind of nanomaterial we put together for aircraft. Started out with Hawaiian Air on a tail section where they had a bunch of corrosion. I started working with United, things we never really even appreciated about the maintenance, what it takes for these things. And now started working with Lufthansa and some others, and of course, Department of Defense, just to manage corrosion. Not what we started out thinking of, but again, this is all developed downtown Honolulu. DragX is kind of an interesting thing. So it's another kind of nanomaterial we put in pipelines. So during the early years of the Obama administration, they were trying to stop methane from leaking. We thought, well, we can maybe take a look at that, and did a collaboration with several companies, and you know, they all put in capital, and it turns out we could stop methane from leaking. And then during the Trump administration, it became uninteresting to look at methane because they didn't want to talk about it. But it turned out we reduced drag in the pipeline about 25%, saves a lot of money. Now what we're doing, which is kind of interesting, I was on a call earlier today where we're looking at, we can create a material to put on the inside of these pipelines to pump the mixing hydrogen into in with methane. But the key problem is you have a thing called hydrogen embrittlement. And that's where the hydrogen molecules get into the metal, and then at some point it can blow up. And we started working on that a little while ago. Turns out we think we can stop that problem. And that means you can repurpose an existing asset and start moving hydrogen. That we think that makes a huge difference. And that looks like it's very promising, but we're actually, I was looking at some pictures here. One of the guys was sending, we're doing a couple miles of pipeline right now, but I mean, literally I think in Texas, but they're going to be using windmills to create hydrogen, pumping hydrogen through pipelines by mixing it with methane to reduce the carbon footprint. And these are the kind of things that are going to be going on in this industry. Now I kind of pivot to another nanomaterial we developed for the military on the left, which really looks at obscuring infrared, to a beauty product on the right, which we're doing with a Korean company. And to scale up around that, we're not really understanding beauty products, but it turns out Koreans really are good at it. And so we have a collaboration where we actually produce a nanogold material and can scale up manufacturing. All that was done here in Hawaii, but you know, we learned how to do that through this other work we were doing. Another thing we started doing is using nanomaterials to create thermal polymers, which sounds kind of abstract and how would you use it? But we thought you can make a cooling garment. And with climate change, it turns out there's a lot of interest in it. So we created a new brand, 19 degrees north, and did a Kickstarter campaign and started producing and selling these. And we've got industrial versions, sports versions, and others. But this came, again, from some of these early ideas in nanotechnology. An application we call nanobes for fighting cancer, which we've done a bunch of work in this space. So designing these little nanomachines. We did some really good work on some tumors and basically stopped the tumors in mice, of course, not a big market there, but really good early work. Designing a nanomachine with a delivery payload system, injecting it into the mouse, and it went and killed the tumors. Nanoenergetics, and I put this up here because this was one of these curious questions we had, you know, as we kind of go through that process in intellectual anarchy. It turns out we can control combustion on a nanoscale and produce a lot of energy on demand. And it's kind of cool. We're not sure what to do with it, but we started looking at making unobtainium with this technique, making materials that can't exist. And we can actually scale up a manufacturing process we're playing with now. And this is the kind of application you can use it for. So, you know, I saw that William Shatner just went into space with Jeff Bezos' system. To get the right kind of material for space travel, it doesn't exist. It could exist. We can create these new classes of materials and look at scaling the manufacturing We've got applications for food, a version you can eat to make food fresh so you can ship it with less refrigeration and keep it fresher longer. Materials to make smart materials. So this is kind of an adaptation of manufacturing called these are smart materials. And so we can put them into, we started out making stealthy materials and then making noisy materials, making sensing materials. You can mix them in with cement, make the cement a sensor. We put this stuff down whole, that's a well on the right. And we went from making kind of cupfuls to truckloads to, we're trying to make freight car loads right now. And we think, for example, we can make quiet sheetrock for construction, and we're planning to do a demonstration, I think, in Korea. Now I'm going to pivot to a new thing, the second area that we're, examples of what we've been doing in disruptive platform technologies. And this is around anthropometric artificial intelligence. And this is really human-style AI. And human-style AI, humans are really good with edge cases, ambiguity. We're not big data guys, we're small data machines, basically. And so we thought, can we make something like that? And so we started out on this journey to do just that because we thought it was really important. There's a lot of, we can get into why that is, but it turns out we're running out of, we look good because we have cheap computation. Transistors are cheap, computation is cheap. Moore's law, the price keeps dropping. We all look really smart, but we still do the same inefficient ways of computing that I probably did when I was a sophomore in high school, frankly. So we thought, let's try this thing. And so we started applying it against some really weird problems. And this is one of them on dark matter. This is a picture of a device in a nickel mine in Canada that's really the brainchild of a Nobel laureate, Art McDonald, who we started working with on this dark matter thing. This is, again, one of these things where we said, we're looking at creating these ideas around high energy physics and dark matter. Are you interested in working with us? And the answer was, yeah, let's try it, because nobody knows how to solve some of these problems. Anyway, I put this picture because it looks pretty cool. It's like something out of Matrix, but it's really a massive sensor that's underground looking for neutrinos, trying to unlock the secrets of the universe. So we started weighing in on this before the pandemic, and we kind of had to pivot since we started making something else, and we're just resource constrained for a while. We're using it as well to look at things around what's going on with competing false narratives. So another thing we're applying it to. A lot of work in cyber. It's got all kinds of cool applications. But we thought, what if we apply it to this area of basically cancer was the question. Why can't we cure cancer? Why is it such a random act? Why is it that some people get it, some people don't? And why do we do this approach to cancer or medicine therapies and other things, these epidemiologic studies, which led us to this conversation, Plato versus Aristotle, this causality versus correlation. Could we develop the mathematics of biology, which we then pitched to DARPA, which they underwrote, and we then developed what we call the grammar of RNA, which is a tool set. So what that means is, you've got 3 billion base pairs, right? And so we can sequence the human genome. It almost looks kind of like a language. Now, this is kind of a mind shift, but just to get your heads around it, when you look at all these letters, it looks like gibberish. But consider that the American alphabet's 26 letters, and letters come together, make words, words make sentences, sentences, can convey ideas. With 26 symbols, you can make infinite complexity. And we said, what if that's really what's going on with genomics and with disease? We just can't understand it. So we started building the machine to understand it. We've done a lot of really good work in that space, but that's what started with that. And we said, these epidemiologic studies, why do I have to, to know that cancer, smoking kills people? I got 1 million people that smoke and 1 million that don't. I watch them for their lifetimes. I compare the data. That's how we do things today. We thought there's got to be a better way. And then on top of that, we thought, why can't we design therapies? based on mathematics, more like an engineer. And we started marching down that path again with DARPA before the pandemic. And then when the pandemic hit, we thought maybe we could do more. So we then took a big pivot to see if we could design something to help with the pandemic, which turns out would be a rapid test. And to get a rapid test into the market, you've got to do the science, you've got to deal with manufacturing and scale up quality systems, and then you've got to deal with regulatory. And we did the science in a few months, which is nothing short of remarkable. We created these organonucleotides that uniquely bound with a part of the virus that you could use for all kinds of things. But once we got into the scalability question of manufacturing, we were trying to build manufacturing here in Hawaii, but it was not to be. We found a manufacturing partner to work with in Korea, but we had to adjust our science to meet what they could deliver, which they've done a remarkably amazing job with. But we had to kind of flip the script and say it's not just about the science, it's how can you really produce it fast enough to get into the market. And then on the regulatory side, we've had a few false starts, but we submitted, I thought, a good data set to the FDA. They pushed back because one of our comparator labs was out of compliance and disqualified some of the data, so we had to go back and get more data. We're just about ready to resubmit. And the test, the process looked kind of like this. And I put this up here because it is not a straight line, not even close. This is normal. And our early on talk about the blue zone and the green zone. Going from the blue zone to the green zone never is a straight line. That's why we call it the rock and roll zone. It's full of all kinds of twists and turns, and not everybody's cut out for that. We have people that live in that space, they're really good at it. It's not for everybody, but that's kind of the process. And this is kind of what we got, and it works really well, and it's relatively inexpensive, and we can scale it. We're in the middle of getting that to market. So at the end of the day, I can go on, but this disruptive technology comes from this environment of the right environment for people, culture, and organization, which I talk about in the book. But it's what enables us to do what we do. So we have to get these really incredible people, and there's no shortage of talent in Hawaii, by the way. That's a unfortunate misunderstanding. The University of Hawaii produces some amazing people as well. So that's a whole nother conversation. Culture in the environment is really important. And creating a culture and environment that allows people to try things and sometimes fail, which most people are uncomfortable with. And trying things that are new, a lot of people are uncomfortable with that. And then organization. The right organization, it's more flat, not so vertically stratified, to allow people, give them that opportunity to become awesome. So anyway, I'll open it up to questions, and as Roger said, I can go on, but that's kind of the quick review of the whole idea of disruptive technologies.
Well, thank you very much, Patrick. One question I think you should explore and explain is, how do you get the people to do this kind of work, and how do you actually manage them in this process?
It's a really good question. It's not so easy, I would say, so we get young PhDs, we have to kind of untrain them because they go through the program and they've solved something that's never been solved. So they're actually all very smart. But we have to get them comfortable with being uncomfortable and not being the expert, because the most important skill they have is how to solve an unsolved problem. And to get them, they're excited but comfortable with learning to learn and learning fast. And this idea of, as I tell them, getting up off the floor when they get knocked down, because they're going to get knocked down. And we have to work with them and tell them, you're going to try this, chances are you're going to get hammered. You got to get off the floor. So we have this process to try to get people over this hump of they can never be wrong. They got to be the smartest guy in the room. And they've got to be willing to learn. And so it's almost like a little bit of a boot camp. but we, as I tell them, you know, before COVID, we'd take the group of young PhDs to lunch or something. I say, look, you know, now your mom's proud of you, we're proud of you, but now nobody cares. What are you going to do that's going to matter? And it's not about just doing what you always did, but the things we're going to focus and work on are going to be things that have never been done. And to get their heads in the game, it's hard. But we find it's really about the right mindset. So we find some of these folks at UH, we find them from universities all over. We recruit from a variety of programs. We work with about 70 universities, so we look for people that we could, you know, maybe we see grad students that are, you know, finishing up and give them a chance if they want to come. It's kind of like if they like this whole thing of solving these really hard problems, they either become exhilarated and they love it, or they're terrified, and not much in the middle. So we kind of put them in that environment. The ones that make it and stay, we call them techno warriors, but they're just in a league of their own. And we have a bunch of those kind of guys, or girls, and but it's a process, and it takes work.
Can you take us through one example? First of all, explain the term intellectual anarchy, and then how it actually worked in one project.
Yeah, so the intellectual anarchy is a process. It's not really anarchy, but what we realized was that we produce things persistently. And so persistently producing things is what made it so interesting, because when I started tracking over and over, so the two examples I gave, you know, the early interest in nanotechnology is produced, it just kind of snowballed into a whole bunch of things, and it just keeps going. So it started out with this question. So for example, I mentioned this nanoenergetics, which kind of goes back, you know, that diagram I put up there. If you look at, I mapped that out actually in a diagram. This question, can I control combustion on a nanoscale? It was a question. And we didn't know. And in the process, we almost blew up the lab, but we learned we could. And what we did was we could produce it, put it in a water mixture, kind of sprayed it on a wall and shoot it with a laser from a distance and light the whole thing up. Now, what we're looking at and still considering is different applications. So we thought, what if I use it as like a chemotherapy? I put it on a tumor with a switch, I can turn on 3,000 degrees on a nano point. So those are things we're exploring, but it started with a question, can I control combustion on a nanoscale? We're also looking at nanopropellants for nanosats. So if I can put it, it turns out it's very hard in space, outer space, the final frontier, you know, with a lot of these solid rockets to give them a little bit of a burst. It's either all or nothing. So we can sort of put out a little bit and get a burst, and it puts out about 7 to 8 times more energy density than TNT. And we can do that on command. So it was this question, can we do it? That's really what led to it. And then we started playing with it, and then we convinced people to fund it, and we started talking to people. We've been talking to NASA about this nanopropellant, where you can put this into these little nanosats, these little tiny satellites that are in different orbits. And so you can push the satellite to a new location by giving it just a little burst, and you can aliquot just so many nanoparticles and then fire it up.
Give an example of the kind of team you put together and what their original discipline was, and how you took advantage of their skill, not their expertise.
Yeah, so we have, it's interesting. We have, boy, an example. So the stuff we're doing with, I mentioned this, creating these organonucleotide molecules, right? So strands of RNA or DNA that could change the way a cell behaves or be a therapy or something. That idea really developed with somebody with a PhD in aerospace engineering. And then we there was no good way to do the mathematics, so we coaxed a couple of high energy physics people to start working on it. And then we got one of the guys here who's basically a virologist. He came in kind of after the fact, not before the fact, because if we put him up front, he'd tell you right away it can't be done. And once we did it, of course, then it's much easier. So we didn't lead with the expert. We led with the people that were curious about it. And then we brought in the expertise to make sure we didn't do too many stupid things. But that's kind of the way we'll do it. So it's not we lead with somebody with a, so for example, if you've got a guy in PhD in virology or pathology or biology or something, and you told him we were going to do this thing to design these organonucleotide molecules, they would probably just tell you it can't be done because it wasn't really done. And when we started this with DARPA, we don't think it was ever done like that. And they threw some problems at us, these puzzle problems, which were unsolvable, intractable problems. And the guys involved, guys and girls involved, was an interesting team: mathematicians, computer scientists, physics, engineering, and life sciences. But again, if we're doing a problem that's going to disrupt the field of life sciences, it's almost counterproductive to spend all your time arguing with an expert about why it can't be done, because they've spent their entire career believing it can't be done. When in fact, once it is done, then they'll say, well, of course. It always works like that, but that's exactly the kind of journey that we go through for all of these projects.
Typically, how long are these journeys, if there is such a thing as typical? What's the shortest and what's the longest?
Well, yeah, I say roughly we're almost always a decade ahead of everybody in our thinking. So 10 years is not unusual. How fast can we move depends on market interest. And the thing we did with that project, that I mentioned, the Macondo blowout, doing that in 18 months was unheard of in the industry. I think Shell, pretty much all the major energy companies and we work with all of them today, that reverberated through the entire industry, that you've got a firm. The fact that we're in the middle of the sea, they all started visiting, honestly, from all over and from the Middle East and other places. And again, we're green energy people, so how does that work? But it turns out we were able to go from an idea, small coupons, to just do the basic, the science kind of works, because we had no idea. So we did the samples here in the lab. Again, this goes to the steel cement interface, and can we improve the strength? We improved the strength by like 200%. And then we sent some samples to Houston, then they sent some samples to Amsterdam, and because they're Dutch, they worked on it, and they were kind of shocked. And then, could you scale it? So they said, we got this thing going in Pennsylvania. Could you do it? We had 3 months to scale it up. We'd never done that before, and built that. We sent a team from Hawaii, mostly young people who grew up in Hawaii with a lot of education, to work in the oil patch, who'd never done it before in their lives. We built a factory. We had help, of course, and the results were staggering. Really, they were so good they thought there was a mistake, and it took months to get all of our results out of them. And then it was, build this factory, which we also did in very short order. So that was relatively quick. A lot of these things can take longer, but the reason they take longer is because we're not really spending time talking to listening carefully to the marketplace. As we started adopting this idea of active listening, which we do in the green zone, and populating the green zone with people that are really good at listening to customers and users, then of course we started accelerating the whole thing. But I say from some of these very early ideas, it's not uncommon. It could take a decade because it's about market timing. So for example, if not for COVID, we would never produce this test. If not for COVID, we would never have had the chance to exercise the ideas the way we did. But the fact, because of that, we pivoted our team, kind of had to pull them off of certain things and put them on that. And the team that really put all that together, a lot of them, you know, physicists and engineers, computer scientists and others. I mean, we were using computing clusters that we could, everything we could get our hands on in Hawaii, even though what we were doing used significantly less computational power to do these models. You know, we'd never done it either. So we actually produced it quickly, collaborated with the University of Hawaii to actually started producing some of these things and found out the results were really good. But they weren't people that spent their careers in that field. And that turned out to be a benefit in the beginning. Once you kind of get into the field, at some point you got to start adding people that know a lot more about the subject.
And are people in the same team until a product is created, or are they in many teams at once, or several teams at once?
It's kind of many teams at once, but the transition and the handoff is always, you know, I call it the rock and roll zone because it's always a little chaotic and messy. So the guys, the early science guys got to let go, and product guys got to start picking it up. And as they pick it up, like to produce a product, you've got to look at quality systems, documentation. It's all the things that the guys in the blue zone don't like, and the guys in the green zone have to excel at. But when they appreciate each other, it's not about pointing fingers, it's about helping each other. And the technology Sherpas, the people that kind of go between those zones, help translate between those two cultures. But the guys in the product side are not the guys in the early development side. They're just not. And we learned this the hard way and many times over. The guys that love the blue zone, the deep science stuff, will hate being in the green zone.
Do you ever abandon projects, or they just lie in wait for a further discovery?
You know, sometimes we'll do something and it won't quite be the result we thought, but then we just kind of let it sit and maybe go back to it later, or maybe revisit it. We've pulled the plug on things as well. So there's quite a collection of things. I mean, we were just talking about it the other day because we encourage these young PhDs to write a proposal. We submit proposals on ideas and be prepared to get rejected because 9 out of 10 times, you know, in certain categories, that's what's going to happen until they kind of get their sea legs. And so we're showing a young PhD, we got some old folders and stuff, but we had a proposal, which I thought was very cool. I went to NASA several years back and it kind of bumped into time travel and how that might work. This is before quantum became a thing like it is today. And I thought it was a cool idea. It was rejected, but we kind of pulled it up and said, you know, maybe we should dust it off. And so what I find is that these ideas, sometimes you learn as much from the rejection or the failure as much as from the success. And you have to look at it that way. So when something is rejected, you got to ask, you know, why? Was it the wrong idea, the wrong audience? Was it not clearly conveyed? You know, all those kind of things. So what we discovered was sometimes a very well thought idea doesn't get support. And sometimes a half-baked idea just gets it. And it's kind of all over the map. So we tell people, unless you are willing to put in something, you're never going to find out. And this is one of the things we do with these young people, because once they get older, a lot of them are afraid of being rejected for fear that they're going to lose their credibility. But I tell them, you're never going to learn anything. I think Einstein was saying, you know, anybody who's never really failed has never tried anything new. And you have to be willing to do that. And people talk about it like it's, you know, of course, it's easy, but it isn't. And that's where, in that last slide that I showed about culture and the environment, that's what I mean, right? Where as long as you're learning something, it's okay. But I tell some of these young guys, the only way you're going to fail is if you don't try. Just because they rejected you, don't take that to heart. Learn from it. Keep learning from it. And the ones that learn to do this get really good at it.
That's marvelous. Well, I think we've swallowed an hour quite easily. And so I'm afraid it's time to bring this to a close, but it's been absolutely fascinating, as always. And attendees will have this up on the Better Tomorrow YouTube series, on their channel, and eventually on our own website in a highlight mode. Though I don't know how you do highlights from what's just transpired here. Anyway, thank you very much, Patrick, and aloha, everyone.
Thank you. Aloha. Thanks, Roger.